All right. Thank you. Thank you. So we got a long talk. I've got my water over here. Gonna try to bring it over here. Maybe it'll be a little closer for me. So we're gonna get this awesome opportunity to go through the Casper family of protocols, and in some detail, which I don't think has ever been done before in terms of like me giving a presentation. So I'm excited. I think we're good to go. So let's take a look at the outline. Can we get presentation mode going? Anyway? There's like a play button there on the right. Is that Lir? Sorry, guys. We'll hopefully be going through this soon. But I guess I could just start. So it's broken up in three kind of parts. The first two parts are really like the meat of the presentation. The first part is like an introduction to consensus, and then the consensus safety proof that all of the protocols that I'm going to specify in the second part, including sharding, are going to satisfy. So the first part is kind of the important part where all the analysis happens and where you kind of get to understand something. And then the second part is protocol specifications and pictures and trying to kind of relate the proof, which is kind of quite abstract, to something quite a bit more concrete, like, for example, like actual consensus protocols, like actually running. So, did you try pressing on the button? So you see the Lir at front? Yeah, just click there. Keep going, keep going, keep going. One more. Bomb.com. All right, settle down. We don't have all day. All right, introduction. What are consensus protocols? Well, consensus protocols, they allow nodes in a distributed network to make consistent decisions, even though in a distributed network, out of mutually exclusive, inconsistent alternatives, they might screw up. So if a node over here decides on something that contradicts a node over there, then like that's like not the point of a consensus protocol, right? The point is for them to like be consistent in a distributed network, and specifically, normally we talk about coming to decisions on the same values. But in sharding, we're not all going to be coming to decisions on the same values, but we will still want a distributed consistency property where, oh, you're not contradicting any of the values that someone comes up with over there, even though you may not all be coming up with the same values. So generally, I would say the consensus protocols of the sharded or uncharted variety are about nodes in a distributed network making consistent decisions. So if I say coming to consensus on a bit, what that's going to mean is like, oh, we're making decisions on a 0 or a 1. And so if you decide 0 and I decide 1, those are inconsistent. If we both decide 1 or both decide 0, then they're consistent. So, we're going to look at a binary consensus protocol, but then we're also going to look at an integer, a blockchain, and a sharded blockchain. And they're all going to be consensus protocols, and they're all basically going to have the same type of property that like, oh, the things that nodes decide about it need to be consistent, even though they're on different points of the distributed network, or in the sharded case, even though they're not even on the same shards. So we kind of have two basic properties that are kind of traditional, kind of mandatory reading. Safety property, which says, oh, the values you decide on are not conflicting, and liveness, which says, oh, you'll eventually decide on a value or reject it. So the reason why consensus is quite hard is because different nodes in a distributed network don't see all exactly the same thing all the time. There's delays, and messages won't be propagated with like 0 latency and infinite bandwidth to all nodes at all times. So nodes will see different things. And that makes it quite hard. And the order of messages might not arrive as expected. And additionally, there might be like other kinds of faulty behavior. So consensus protocols are kind of classified by the adversarial behaviors in which they can survive. And more specifically, where their safety and liveness can survive. So we have this great result in consensus protocol research called FLP impossibility, which basically says that, oh, look, if you have an asynchronous network, you can't have both safety and liveness if there's a single node that's faulty. if your protocol is like deterministic and doesn't use any cryptography. Basically, the way this kind of works is, at any point you're trying to make a decision, and you can only do it if everyone is kind of aligned with you. But in asynchrony, there's always going to be one pivotal node, and they managed to show this in the paper. But for our purposes right now, all I'm saying is, oh look, I'm not going to show you an asynchronously live and safe consensus protocol. I'm just going to show you an asynchronously safe one. And that kind of leaves off the intro, like just basic consensus protocol section. I'm going to take a sip. All right. So now what we're going to do is we're going to give a safety proof, a consensus safety proof for a protocol, and then specify the protocol, or then kind of specify enough of the protocol to prove the thing. But the first thing I should mention is, okay, what is this approach? Well, it's called the correct by construction approach to protocol design. And instead of basically like specifying a protocol and then doing the analysis of proving that it has all the properties that you want, the way it works is you specify a little something about your protocol, then you say what properties and proofs the protocol should satisfy, and then you derive the rest of the protocol to satisfy those proofs. So you kind of set up the proofs first, and then you kind of pull out the rest of the protocol in order to guarantee that the proofs are satisfied. So we kind of try to do the analysis first, and then the protocol specification second, in order to make the proof of the protocol's correctness really, really simple, really, really easy, because like the whole protocol was designed around the proof, and the proof was designed to be like as simple as possible. So, traditionally, okay, you do protocol first, analysis second, and now we're going to try to do analysis first and protocol second. This is kind of a heuristic. It's not really exactly what correct by construction is, but it's a good way to think about it. We kind of reorder the presentation somewhat to give the proofs first and then the protocol in such a way that kind of falls out of the proofs to satisfy it. So now I'm going to go through this proof, separate it out into two parts, and the first part is going to be very kind of trivial, and the second part is going to be like super interesting and less trivial, but we're going to take them both in like significant detail. Yeah. Don't always get to do this. So we have a protocol. It's got some protocol states. It's got some protocol state transitions. I'm representing them as these little nodes with arrows. The nodes are states and the transitions are the arrows. And basically, they describe how nodes evolve in the protocol. Protocol state transitions, we have like, we have an identity and transitivity. So if there's like a transition from A to B and a transition from B to C, then there's a transition from A to C. So like, if the protocol could evolve from one state to another to a third, then it can evolve from the first to the third. It's kind of some trivial properties that protocol executions happen. So I haven't drawn it here, but for example, there's got to be a line from like the one in the bottom left to the one in actually that's not a good example. The one in the middle to the one in the top, even though it's not drawn. So in the binary, we also have something else, something called an estimator. So we have these protocol states and protocol state transitions. Okay, that tells us almost nothing, right? And then I'm going to give you a little more. We have this thing called an estimator, which maps the protocol states onto values of the consensus. It basically says, oh, from this protocol state, like this is kind of what we think the consensus is. It kind of associates the states with values of the consensus. So we have a little more in our protocol now. For example, in a binary consensus protocol, we're going to map the protocol states to bits. In a blockchain consensus protocol, we're going to map the protocol states to blockchains. It kind of corresponds to the blockchain protocol like a fork choice rule. Your node is at some state, it's seen some blocks at certain times maybe, and then it will like pick a blockchain out of them. And this is like a map from like the node state, which represents like it's like the state of software at the time, to like the particular blockchain that it chooses when it's in that state. So the estimator kind of maps protocol states to values of the consensus, but it's not like they're necessarily decisions, but they're just kind of like estimates, right? They might be revised in the same way that a fork choice rule is. So we also have a kind of system of types for reasoning about consensus values. We can just think of this as like propositions about the values of the consensus, like, oh, that's one, this blockchain has this block at that height, because there might be a whole bunch of blockchains that have that block at that height, and we want to talk about the fact that this block will always be in our blockchain in the future, but we can't say that, oh, we'll always have this blockchain. And so we need to talk not just so directly about consensus values, but also about like maybe properties of them. So we're kind of able to do that. We have a type system on the values of the consensus. So then we have this notion that like the value of the consensus satisfies a property, right? And I write like C implies P if like the type P or the proposition P is satisfied by the value of the consensus. So for the estimator, we can basically talk about whether the estimator satisfies a property. Great. So we have, again, protocol states and transitions and a map from them to values of the consensus. And now we also have this system for talking about the values of the consensus. Finally, we have this definition here, which is going to be like the last definition before we can really step into our proof. It's called estimate safety. It basically is a local notion of safety that says, oh, look, for some proposition P, it holds for the current state and all future states. So it's a function of a proposition and a state, and it says that, oh, look, that proposition holds for the estimator and all future states. So any way you can follow these transitions down, you'll only get to states which map to value of the consensus, which entail this proposition P. So when something is safe, it's kind of invariant over all future protocol states. So I have a little example here. All of those ones are safe because each of those ones there, all of their future states have a one also. The zeros there and the nodes in blue have future states which are not just the values that they have there, and so they're like not safe. Now this particular protocol state transition like object here doesn't correspond to a non-trivial consensus protocol. It's very trivial. The only thing you can decide is one, really. But it kind of shows you the idea of like, okay, all future states have the same value. So we have this consensus safety proof, basically the first part of the consensus safety proof now that I can present. Basically, it says it's composed of kind of two parts. One of them notices that, okay, well, if a proposition is safe here and we have a state transition to some other state, then it's also going to be safe there. Which makes sense because all future states of the first one have that invariance. Any future state of the second one are future states of the first by that transitivity property that we talked about. And then we have backwards consistency, which says like, oh, if I have safety here, then there's nothing downstream of this thing that was safe on its negation. So it can't be that there was a previous protocol state which was safe on the negation of something that is safe in this protocol state. Because if it was, then the forward safety would mean that like the negation of that statement would be safe, which is exactly what we assume that the statement is actually safe. So basically, in our setup here we have a laser. Anyways, in our setup we have safety at sigma 1 on P. That gives us safety of sigma 3 on P. And the second result gives us safety of not P at sigma 2 at the bottom there. So if at sigma 2 not P was safe, then not P would have to also be safe at the top there, and we get this contradiction. And so kind of our result here is basically that if we're safe at P with P at sigma 1, then we're going to be not safe with not P at sigma 2. So this is kind of a little subtle, so I'm going to talk about it a little more. So you know, if you are a protocol state and you're safe on some proposition P, then you follow some future path to some other state, and then you walk backwards to any other state. Then for that other state, you're not going to have safety on the negation of P. So basically, any state that's downstream from anything that's upstream from you as a protocol state when you're safe on P is not safe on the negation of P. And this is going to be really useful because we're going to be able to interpret this as consensus safety. So firstly, we can do a little bit of logic here and show that this is equivalent to the fact that it's not the case that P is safe at sigma 1 and not P is safe at sigma 2. You could also think of proving that if you assume that they were both P was safe on sigma 1 and not P was safe at sigma 2 and have a future state in common, sigma 3, then there both P and not P would have to be hold, which we're not allowing. So in some way, this looks a lot like consensus safety. It means like, oh, look, the things that are safe there and the things that are safe here don't contradict each other. They're consistent. You know, and the nice thing though is that this distributed safety property isn't a local property in the same way that a node's state is. there's lots of other protocol states there, and basically our interpretation is going to be that we're going to make decisions only on things that are safe, only on values that are fully covered by the things that are safe, so that we can take advantage of this property. So as long as nodes all run protocol states in this state of protocol states and transitions, then they can have a common feature state. So before we were just thinking about it as kind of one node running through the thing. Now we can imagine, we have multiple nodes running through this protocol state transitions. And if they have a state in common and they only decide on stuff that's safe, then they get to have consensus safety. Because all the stuff they decide on all holds in their common feature state, and therefore is consistent. So basically, you're allowed to make a decision if it's on a safe proposition or if it's on a value that only implies safe propositions. And if you do this, and if nodes have a common feature state, then this distributed consensus property, this distributed safety property is the same as consensus safety. If two protocol states have a common feature in common, that means that two nodes at those states who only make decisions on safe estimates have consensus safety. And that's essentially the key result and like the point of part one. So nodes who only make decisions on safe estimates or that are entailed by safe estimates and who have common feature protocol states in common have consensus safety. And the reason, if you have a common feature protocol state in common, then all the things that are safe locally are going to be all safe together at that feature state, which means that they're consistent. So this is that's the part one of the proof. Assume that nodes have a common feature state, assume they only decide on safe stuff, where the safe is this local notion, and then we can show this distributed notion of safety. All right, so it's kind of important. This is like, if you don't get this, it's not going to make much sense. So nodes, if they share a common future state, have the property that anything that's invariant in all their future states are consistent, because those things that are invariant all hold at their common future state. So I'm going to go for another drink now. Thank you. So with part two, we're actually going to be guaranteeing that nodes have a common future state. In part one, we assumed it, and it's kind of not that satisfying. So in part two, we're going to try to make sure that as long as there's not more than some number of Byzantine faults, then we're going to have a common feature protocol state. But first, what are these Byzantine faults, and why does it matter? Well, if you have a non-trivial consensus protocol, then you'll have some nodes that are safe on 0 and some nodes that are safe on 1, for example. Or you'll have mutually exclusive outcomes which nodes could become safe on and decide on. And this is kind of an issue because, if you're a node going through protocol state transitions here, you end up on the left and I end up on the right, then we have consensus safety failure. And, and our theorem doesn't hold because we don't have a common future protocol state. So non-triviality basically means that there are some states which are safe on mutually exclusive values and that they're accessible somehow. And so that means that it must be possible for you to get to a state where you decide on 1, and it must be possible for you to get to a state where you decide on 0. However, and it must be possible for me to go to 0 and me to go to 1, but somehow we have to coordinate to each end up in the same place. So it's just kind of not necessarily trivial. We can't independently follow our state transitions. We need to somehow be having some kind of signal in common, some kind of interaction in order to make sure that we're following the same, or that we're making consistent choices in this environment where we have mutually exclusive outcomes. So we're going to assume that we have named nodes that can send us messages that are signed. And then basically what's going to happen now, these are going to be our consensus forming nodes, and then anyone in the protocol is going to know about them and is going to watch messages from them in order to try to decide whether to go down this way or that way in order to not be kind of screwed, right? And then as long as these nodes are showing you kind of the same thing that they're showing me, then we may have some hope to end up on the same side of this mutually exclusive branch. So we really did need some kind of assumption here, and this is the one I chose to make because it's useful in proof of stake, and so but we could also talk about proof of work, but this is not today, right? So we're going to assume that we have everyone knows who the nodes are that are forming consensus, and they all can sign messages, and they all do sign their messages. And further, your protocol state transitions only occur when receiving signed messages. So like your node is just going to stay in the same protocol state until it receives a signed message, and then it'll transition to a new state. And so now we have understand that our okay, even though we're just looking at this as a lattice, we're going to actually be able to have some more complicated structure here in terms of the way our protocol states look. And so we were talking a little bit about Byzantine faults, and it's kind of important because Byzantine faults can screw this up pretty badly. If all the nodes that are consensus forming run a version of the protocol for you and a version of the protocol for me, then there's no way to guarantee that we're going to make consistent decisions. At least like one of the nodes that we're looking at in common has to be the same, showing us consistent things. So if there's too many of a certain kind of Byzantine fault, then we can be screwed. And I'm claiming that, oh, look, equivocations are a kind of Byzantine faults that are fundamentally good enough for doing this. Equivocations correspond to a consensus-forming node not behaving like they're running the protocol once, but behaving like they're running it at least once, like more than once. So any behavior that can't be produced by a single execution of the protocol, but can be produced by more than one, is considered equivocation. So these two green nodes here, maybe you can imagine them as sign that we received a message from these nodes that said, oh, look, I'm there and I'm there. So the same node sent both those green nodes. Now that's not an equivocation because there exists a path through the protocol space that hits both of them. Whereas the red ones, if I receive a message from a node and the red one on the left and the red one on the right, those are not honest behavior. That's not honest behavior at all because there's no single protocol execution that could have produced that. You need to actually execute the protocol twice to get to both of those states. If you're going to execute the protocol correctly. So somehow, rather than considering all the arbitrary behavior, we're going to focus on this equivocation fault, which just corresponds to correct execution of the protocol, but like more than once. So this more than once kind of execution of the protocol is going to allow our consensus-forming nodes to tell me to go over here and you to go over there, so that we're forever separated and have like consensus safety failure. So that's it's kind of a problem, right? Why there's no way for us to have consensus safety in the context of 100% Byzantine faults. It should be pretty clear, because we have to have a straight state transition to something with P, and we have to have a state transition to something with not P, and we can only really count on these nodes, which might be telling me to go to P and you to go to not P. So we have to kind of assume that there's going to be less than some number of Byzantine faults for consensus to work out. But that's okay. We're kind of used to fault tolerance numbers of less than 100%. So we're gonna try to figure out then how to make sure that nodes have a common future, as long as there's less than some number of Byzantine faults. So we know kind of that we can't possibly be non-trivial and have them have a common future if there's too many Byzantine faults, because if they have a common future even with 100% Byzantine faults, then it must be the case that every two states have a common future. So we need to make sure that we have a common future, but not if there's more than some number of Byzantine faults. Well, let's start by counting Byzantine faults, right? We're going to count these equivocations. So from a set of messages from a validator, we can literally just check whether there is a single protocol execution that goes through all of them. And if there is, then that's not an equivocation, and if they're not equivocating, and if there isn't, then they are equivocating. If we have a bunch of messages from a bunch of senders, we can tell which of them equivocate. This is kind of assuming that the messages say, look, I'm at this state. Look, I'm at this state. And if the validators have weight, like they do in some consensus protocols, and then we can talk about the weight of the equivocations, not just the number. So somehow, okay, we have this definition which we can actually use to count equivocations from sets of messages. As long as the messages say, oh, I was at this state when I sent it. Oh, I was at this state when I sent it. So this is kind of like tying the knot here, getting close to the punchline. So we're going to let protocol states be sets of message that exhibit less than some number of Byzantine faults. So the protocol states themselves are sets of messages that say on which protocol states you were at. But those sets of messages exhibit less than some number of Byzantine faults. Why would we do this? Well, I mean, it's quite clear. But I'm gonna like tease around a little bit. So firstly, like, okay, yeah, I kind of mentioned this. Like, every message says what state you're at, and when you receive a message, you move from a protocol state which has the current set of messages to the current set of messages plus that new message that you received, as long as that new message doesn't tip you over the T faults. So if that new message tips you over T faults, then actually we're not going to transition to a new protocol state. So because the protocol state is a set of messages, you know, this adding a message, receiving a message corresponds to taking a union. I'm just denoting as plus. Every arrow in this protocol state graph will correspond to receiving some sets of messages, such that the number of Byzantine faults that are introduced in that set doesn't go beyond some threshold. This is kind of like a little demonstration of a protocol state transition. So this is like a set of messages over there from 3 validators, line them vertically with like different values of the consensus of those states, and then there was like a message that just appeared in our view that said, look, oh, my state that the second validator had in their message is like the bottom 2 nodes, and the state transition that we took kind of from the set of message on the left to the set of message on the right didn't introduce any Byzantine faults, so we know that it's actually a protocol state transition between protocol states. So an interesting thing is that any message is actually an equivocation with respect to some other messages that like may or may not exist. So whenever you make a message, you actually drop a whole bunch of protocol states with which you used to have a common feature protocol state, which you now no longer do. So every time you receive a message, there are states this set of messages no longer has a common future protocol state, namely the ones such that that message that you just received pushed you over the edge of the number of Byzantine faults that we tolerate for the union of those two states. It's a bit hard to wrap your head around, but the idea is that like by independently making a decision in this protocol space, you are precluding a bunch of protocol states that would only be material if you equivocated, or if you're the one making this message. So you can kind of make an independent decision locally, which ends up bifurcating the state space in the sense that it creates it deletes the common future between different states. And so you can kind of locally make a decision which kind of splits the protocol space in a way that normally consensus protocols would try to coordinate every kind of split in the protocol space. We try to all agree before we take it. But this kind of gives you like a little hint at like what's going on in the kind of in the background. So basically, but the main point is this, right? 2 nodes will have a common future state as long as the union of their views exhibits less than some number of Byzantine faults. So if your view and my view, if we were to send them to each other, so that we had the union of our views and we didn't see too many Byzantine faults, then like that union represents a protocol state that we can both transition to, and therefore you and I have consensus safety. So basically, if there's not more than T faults, then we have a common future, which is kind of what we wanted. Basically, as long as there's no more than T Byzantine faults in the actual network, the nodes will actually only ever visit states such that their union exhibits less than T Byzantine faults, and therefore will have this consensus safety due to the property of having common futures. And the flip side is like, oh, look, if there's consensus failure, that means that nodes didn't have a common future, which means that the unions of their states exhibited more than some number of Byzantine faults, because otherwise that would be a protocol state and they would have a common future. So somehow, by allowing the states of the protocol, the states of this weird protocol states and protocol state transition graph, or to be sets of messages which say what protocol state they're at, which exhibit less than some number of Byzantine faults, like allowed us to make sure that nodes have a common future as long as there's some number of Byzantine faults. And it's kind of really quite elegant, because the only thing we really know about the protocol states at all is that they say where they are so that we can measure Byzantine faults. like I haven't said anything else. So somehow I went through the process of like, okay, I set up the proof at the first part, which I wanted to satisfy, and then I came up with like a construction that satisfied it, rolling out the specification a little bit more. So first I say, okay, look, we have protocol states and transitions, this estimator, this definition of safety. If nodes have a common future state, then they have consensus safety. And then we go and say, look, let's guarantee that nodes have a common future state by making protocol states themselves sets of messages that exhibit less than some number of Byzantine faults. Because the Byzantine faults were the fundamental thing that stops us from having a common futures. And so they're also the fundamental thing that can keep us having futures. Because if we can detect them and know there's not too many, then we can always kind of safely remerge. So that's the end of part one. That's the part with the analysis and the kind of math. The part two is more like protocols. Still some math, but not much. Yeah, if you guys want to take an opportunity to leave and come in right now, that's fine by me. If you have any questions, also would be happy to take it right now. Yeah. Oh, Rob, hi. Hi, Rob.
Yeah, should I get a mic or can I?
I'll repeat your question.
So, determining equivocation, we need some computation over the messages in a state, right? So, couldn't this have the caveat that you could somehow force this computation to be prohibitively expensive?
Yeah.
Very quickly, a message that requires a lot of computation to then determine equivocation. Can we reason about classes of messages or equivocations where this isn't prohibitively expensive? How restrictive are
Yeah. Great. Okay, great question, Rob. So the question is like, oh, look, can we, like, is it gonna in some cases be prohibitively expensive to check equivocations? Because like, oh, look, I mean, if we have like an arbitrary DAG and we have to check if there's a path between two nodes, that can be quite expensive. So, you know, I mean, the answer is like, yes, there are, and yes, this is interesting research, but also all of the stuff that I'm specifying here isn't designed. It's not. It's more like the kind of semantics of the implementation, as opposed to actually how it's implemented. So in an implementation, we're going to have things like sequence numbers, and it's going to help us a lot at making sure that we don't unboundedly go in weird directions. But the way that things are implemented so they don't blow up is kind of a separate topic to how are the pieces of the protocol like factored and understood in terms of the consensus safety proof. So like even with, you know, you can so we can modify protocol states and messages to include more information and still satisfy the same proof, right? So somehow the benefit of this, and we'll see this as the talk goes, is that we can easily change the protocol without changing the proof, because the proof kind of applies at this kind of abstract level. And so we can add things to our protocol message to make actually these checks efficient, and like we do in practice, because in practice we can't be doing crazy things. But in theory, definitions can be like, you know, like you can do all sorts of really inefficient stuff because it's just a definition, and you never actually need to compute it. Yeah, great. So there's a lot of actually potential concerns that if you just look at the construction, you'd be like, oh my God, this is all going to be computable? Like, is this going to be practical? But don't worry, it'll be practical. So for each of these protocols, what we're going to do is we're going to define protocol messages and the estimator. And that's pretty much about it, because by defining what the messages are, and defining what the estimator is, we basically give everything that that wasn't specified already in the at least in like the main piece of the proof. So we're gonna do this for the binary consensus, and then for the integer consensus, and then for the blockchain consensus, and then we'll talk about some other things before doing it for the sharded consensus, for the sharded blockchain. So let's go for it. So the binary consensus protocol has, the messages have three parts. There's like an estimate, which is like a 0 or a 1, sender, which is like this name of this consensus forming node, and a justification, which basically is like a protocol state, or if you're implementation focused, you might think of it as a fingerprint of a protocol state. But for us, it's just a set of messages, namely like the set of the state that the node was at when they sent that message. The set of messages is quite simple. Basically, you have a bit, a sender, and then another set of messages. So any message has that shape, and then it kind of bottoms out at the empty set. So like the messages at height 0 have a bit, a sender, and an empty set. The messages at height 1 have a bit, a sender, and then a set of messages at height 0. Messages at height 2 have a bit, a sender, and a set of messages at height 0 or 1, and so on. And you can kind of define the set of all these messages that have bits, senders, and then sets of messages. And then a couple definitions that we're going to need, and then we're going to keep reusing. So a message is in the dependency of another if it's in the justification. You might think, oh, well, if these sets are not really necessarily going to be the whole state that they were in, because it wasn't really required by the equations on the left, even though I said it on the equation on the right, even though I said it on the left. Then you can think about going in their messages, justifications, and their justifications, and kind of doing this closure. But basically, if a message is kind of down, like causally before another, it's a dependency. A message is called a latest message if there's no message which it is a dependency of. So all of these protocols that we're going to look at are going to be only a function of the latest messages from the consensus forming nodes. Like if you see their latest messages, you'll just ignore all the other ones. So we need to have this notion of latest message. So the binary estimator is pretty simple. It basically will, but first we have to define a score, and the score is basically the weight of the validators who have a latest message with that estimate. So if the latest message, if like 3 validators with a total weight of 20 have a latest message with an estimate of 1 in some particular protocol state, then the score of 1 will be 30 in that particular protocol state. And then the estimator basically says, oh, look, we're going to pick the one with the higher score. If more validators by latest message say 1, then we pick 1. If more validators by my latest message say 0, then we pick 0. So there we kind of have it. It's kind of boring, but we have protocol states, which were these like sets of messages of the form, bit, sender, protocol sets of messages, and then estimator, which maps sets of messages to 0 or 1, depending on whether the latest messages from those sets have more weight according to the senders on 0 or 1. So it's pretty simple estimator, pretty simple protocol states. If there's a tie, it doesn't really matter. Actually, we can do pretty much anything. We can throw an exception. We can use propositions, non-deterministic choice, always return one or the other. These are all various options that I've tried at various stages, and it doesn't ever end up ever affecting anything. This is how we might represent a protocol state for the binary consensus protocol. We have 3 senders, V1, V2, V3, and they've made some messages. So this is representing a set of messages. There's 6 messages in this set. Interestingly, the 2 messages by the first validator are an equivocation because there are 2 messages, each of which have an empty justification. And you can't be at an empty state twice, because after you produce a message, you move to the state where you see that message. And essentially, this kind of shows you the messages and their estimates, so the senders, the estimates, and the justifications. Right? The justification is any set of messages that's kind of downstream from them. The sender is the vertical position, and the estimate is the bit. We can, this looks pretty because I drew it up somewhere nice, but this is a simulation, a little clip from a simulation, where basically, so somehow, at this state, it turns out that like 0 is safe, meaning that there's no way we can add messages to this state, at least without any Byzantine faults, in order to change the majority from going to 0, from 0 to 1. Right? And then somehow this local notion of safety that I can't pass around messages locally to cause a change from 0 to 1 it's the local notion of safety that we're going to use to get our distributed notion. So and basically we're going to like watch a little simulation here, And these are basically nodes running this protocol. Whenever they make a message, it's because it's the value, the bit there is the max weight given the latest messages in the justification. Eventually, these nodes start to notice that these messages are safe. At which point they're not going to change their minds, but they still make messages. If we make messages in like a round, we also we get consensus pretty quickly. Now this is actually, so I'm using a safety oracle here that doesn't detect safety quite as quickly as it happens, but we'll talk about safety detection a little bit later. Also another one of those things that you should worry is maybe intractable because you have to look at all future protocol states. So now we can talk about the integer consensus. It's very similar to the binary consensus. We have some set of the protocol states are sets of messages that exhibit less than some number of faults. This time the estimate is an integer, but we have a center and justification exactly the same way. Instead of using this max weight by latest messages, we just use the latest messages and do a median. The median is just a justifying estimator, right? You take your protocol states, you look at the latest messages, you have from each of them an integer, each of the validators you have a weight, so you can do a weighted median. And we can watch that happen too. This might be useful for something like timestamping. Who knows? It's like a consensus protocol that replicates an integer, right? Normally people think about consensus protocols that replicate some kind of like sequential state machine. But what I'm hoping to kind of show with this approach is like, oh, by giving different values to the consensus by we can generate different consensus protocols that all have consensus safety for, even though they're replicating radically different kind of stuff. Cool thing here is like, oh look, this value 78 that we came up with was never proposed by anyone. Oh, it was, never mind. Sometimes they come up with values that were never proposed by anyone, but not this time. Because of like message arrival stuff. This is like doing rounds. So then the other thing that's kind of nice about this whole thing is like I'm not really bound to any particular message shape. Any set of messages will do, and I consider all possible ways that I could add messages. There's no real synchrony assumption. There's no restriction on doing rounds or forks or anything like that. And we're going to see this more now at the blockchain. So with the blockchain, we have very similar protocol again. The protocol messages have estimates, senders, and justification, but this time an estimator is going to be a pointer to another protocol message, which is kind of understood as like the pre-block pointer. So from any message, you can follow the pointer down to the next one, to the next one, to the next one, all the way down to like the genesis block, or maybe one without a pointer, or the points to the empty set. In this case, it's again exactly similar. We don't really need to reason again about consensus safety because we know that we have consensus safety because we only visit protocol states that exhibit less than some number of Byzantine faults, and that's enough. And so let's define this estimator. We have to define basically a fork choice rule that maps the sets of blocks that we have to a particular blockchain out of there. We're going to use the ghost, right? It's Casper, the friendly ghost, right? It's the greedy heaviest observed subtree, originally by like Aviv Zohar and Yonatan Sompolovsky. Sorry, I'm not sure. So basically the way the ghost fork choice rule works is you start off at the genesis block and you go and you look to see if there's any people who built on it, and if there's only one, you just kind of go there. And if you look at that block, you see if there's anyone who built on it. If there's only one, you go there. And at some point, you get to the split, where you have two options about which block to follow down. And whenever you have a fork like this, the greedy heaviest observed subtree rule basically says, oh, look at the subtrees on either side and pick which one's heavier. In our implementation and in our spec, all these protocols only work based on the latest messages for the validators. And so we just look on, based on the latest messages, whether the validators by weight are on one fork or the other. So in this case, the first two validators are on the left fork, and the right three validators are on the right fork. And so like let's assume that the right three validators have more weight, and so therefore a fork choice rule will go right at that first juncture. And then at the next juncture, it depends on whether validator 3 has more or less weight than validator 5, but let's assume that he has more, and then so then our fork choice rule will be this fork that kind of goes like that and ends in the middle block. So that's kind of the estimator. It's basically like another one of these functions that maps protocol states to some kind of like average or election or like little, in our case, it's a fork choice rule that like the validators would kind of all pick the same forks if they look at it. And the important thing about these estimators is kind of that if validators, if the latest messages all agree with an estimate, then the estimator also returns that estimate, or is also kind of close to it, so that we don't get unstuck. So imagine if we had done, say for example, binary consensus, but with instead of using the max weight, we use the minimum weight. Well, that wouldn't really work, because you would, whenever you get to any state where a majority had the same value, they would move to the other value, and then so basically you would have this kind of constant like adoption and abandonment of values. So somehow I'm comparing this ghost rule to like an average or this max weight function, and it serves the same role in the protocol. And this is going to be very similar to the other protocols in terms of our visualization. The messages from the same nodes are aligned vertically. Only now, instead of having the like integer or the bit in the node, we're going to use this blue line, or sorry, this dark gray line in some cases. The dark gray line, possibly blue. Blue if it's on the latest message, dark gray otherwise, to indicate where the previous block pointers are. So the previous block pointers are the estimates associated with these messages, and every one of these messages, basically like before, kind of has to have an estimate that is justified in the justification. So like the value in the estimate has to be the value of the estimator run on the justification. So if you build a block somewhere, you include in the justification the proof that you're building this on the end of the fork choice rule in your view. So we kind of have a relatively high degree of accountability to where you're mining, because if you mined here, and we saw that you previously mined there, and the view there says that that's the higher score fork, then like that's kind of an invalid block. You're not really allowed to make it there, because every fork choice, every time you make a estimate, it has to be justified by the estimate and the justification. So the estimator is, maps protocol states the value of the consensus. In this first part of the data structure, we put a value of the consensus. And so we want basically the estimator and the justification to be exactly equal to that message, exactly equal to that value. And here's like an animation of this blockchain consensus protocol, just kind of doing its thing randomly, just like in a random message propagation order, and eventually finding some safe blocks. Safety detection, again, is like coming up next. And basically it has to do with like, how do you actually tell when things are safe? And the reason why I left it out is because like, we're gonna have the same safety oracle for all three of these protocols, and looking at them is gonna help us a little bit. Here's another one. If we make a round robin, we get to this really nice thing that I always like to show off about, where we had a really, really low overhead for Byzantine fault tolerant asynchronous consensus, where like every additional message at some point causes a block to jump over the fault tolerance threshold, meaning that like asymptotic cost of consensus goes down to one block a block. Assuming that you're able to make this nice round robin shape, which may be a big if. Now we're gonna talk about our safety oracle, which is gonna tell us when things are safe. But first, a little water break. Any more questions? Oh yeah. So the question is like, is this like a dynamical system, and do I have a convergence? The answer is I don't know, and hopefully. I'm not really a dynamical systems guy. I can't really, but I do think that there are like definitely parallels of the kind of attraction that you need in an estimator in order to create safety. But I can't really comment. I'm not really a dynamical systems person. Yeah. Hi. Yeah, that's right. So the observation was that like, there's no non-determinism, so are we sacrificing liveness? And basically, yeah, I mean, I kind of said at the outset that it's not going to be asynchronously live. However, I have a section on liveness. I'm going to tell you about the liveness kind of it. It's live in synchrony and partial synchrony, but there are reasons why I'm not comfortable with any of the solutions that do use like threshold signatures or whatever to get asynchronous liveness. And I'm going to come to that soon. How are we doing on time? Great. We're still doing good on time, you guys. Awesome. So we have a safety oracle here that I'm going to share with you. But first, a few words about safety oracles. So safety oracles are basically what we call these programs that try to detect whether or not a given proposition is safe at a particular protocol state. There's somehow it actually wasn't necessary in our construction at all that we detect safety in order to actually become safe on these propositions. But if you don't detect it, the consensus protocol can never actually tell you if it's ever decided on anything. It's kind of an interesting thing that you can have a consensus protocol that like makes decisions all the time but doesn't know about any of them until it detects them. But the things that we use to detect them are called safety oracles. And there's an idea of an ideal safety oracle, which kind of does a perfect job of determining safety. And we kind of liken it to executing the ideal adversary, which does a strategic search of your protocol future states for one that disagrees with the estimate you're trying to say is safe. So it will search your protocol future states for like specifically the ones that will negate the thing you're trying to say is safe. I used to actually implement adversaries that basically like do actually operations on the protocol state in order to try to change the estimate, which is really cool, but computationally not the nicest. And so what we look for instead is oracles that are kind of lower bounds to the ideal oracle, oracles that like whenever they say we're safe, we're actually safe, but which are much easier to compute, and which, in practice are like detect safety plenty of the time. So we're gonna define the clique oracle that's gonna hold for a class of protocols with basically these estimators that have this kind of majority agreement property, where if you have like a bigger group of validators over here than over here, and like this one all thinks on all agrees to some estimate, and those ones all believe the opposite, then your estimator is going to agree with the majority. So there's a kind of a precise agreement with the majority estimators, where we're only looking at latest messages that this safety oracle is going to work with. So we're going to basically define this notion of like agreement between estimates. So in an integer, it's pretty straightforward. In an integer or a bit, it's straightforward. Okay, they're the same value. But with a blockchain, it's a little more complex. We say that a block agrees with another if it's in the blockchain that you can find it by resolving the pre-block pointer. So it's kind of blockchain membership. So you will agree with my block if you choose a block which has a blockchain that includes my block. So this notion of agreement is going to be important for our safety oracle definition. It basically goes like this. Okay, well, we have a clique of oracles, a clique of validators that have the following property in some set of messages. Each of them have a latest message that agrees with the estimate in question, the one we're testing the safety of. Each of them see each other agree with that message, and they can't see a new latest message from each other that doesn't agree. So they all see each other agree. They all have, and they can't see each other disagree with a new latest message. So if I have a set of messages, and Alice sees Bob agree, but in my set of messages there's a new later message from Bob which disagrees, then that would like rule out Alice and Bob from being related in this cliquey way that we're talking here. So if we find one of these cliques where all of the validators see each other agree and they can't see each other disagree, then if they have more than half of the weight, then firstly, no matter how much weight they have, they can't really convince each other to change their estimates because of the nature, because they can only send each other messages that agree and can't see from each other messages that don't agree. But if they have more than half the weight, then they also can't be convinced by validators outside of their set, outside of the clique, because they have less than half the weight. And this is all assuming no equivocation. We'll kind of get to equivocation in a second. Then you'll be safe. You'll be locked on this value because this majority sees themselves agree with it, can't see each other disagree with it, and therefore can't be convinced by the minority because the minority has less weight, and it would take some disagreement from within the majority, but the definition of the clique precluded that because you can't see disagreement from inside the clique. So if we have some clique with some weight W out of W subscript E with out of some total weight, then actually we can reason about the fault tolerance, and it's basically like not more than 2 times the weight of the clique minus the total weight. And this is like precisely corresponding to the overlap argument for consensus protocols, but we have to reason about it slightly differently in terms of creating a larger coalition of nodes which agree on some conflicting estimate. So if you have some group of weight W here, if you want to change your mind from that the estimate they all agree on E to like not E, then you have to see some group that's bigger than that. And so we do this kind of overlap argument. We're basically, okay, well, we have a majority WE, the minority is WT minus WE. We need to add to that minority until we get to something that's bigger than WE. And that's what this kind of equation here, WT minus WE plus F greater than WE means, right? It means like, oh, look, we're going to add some number of faults to the original minority. And these represent equivocation faults from the majority in WE. So that we have more weight attacking E than defending it. And so that's kind of like our fault tolerance number. It's like very normal kind of fault tolerance number. But the interesting thing about our clique here is it like the notion of our clique doesn't have any rounds in it, right? It just has the notion of latest messages and agreements. And leads us to our next kind of topic here, subjective fault tolerance thresholds, which is going to help me address your liveness question, actually. But first, a water break. I'll take another question, too, if anyone has one. All right. Well, subjective fault tolerance thresholds. One of my favorite things in consensus protocols, which I've never, which I've been fighting for as long as I knew it was an idea or like an aspiration, but which I like can finally do very reliably. It's basically subjective fault tolerance thresholds means like, oh look, the fault tolerance that I have when I'm running the consensus protocol and that you have when you're running the consensus protocol are not the same. I run the protocol at my level of fault tolerance. You run the protocol at your level of fault tolerance, and you won't fall out of consensus safety with more Byzantine faults than I will if you're running at a higher fault tolerance threshold. It might take you longer to decide. You might never decide if you're running at a fault tolerance threshold that's too high. However, you also won't be, you will tolerate many more equivocation faults for anyone else who also has that level of fault tolerance or more. So basically, if I have the set of protocol messages for any of these protocols is defined kind of independently of the fact that you can count faults on them. And so if we define the same set of messages, and you can count faults and exclude them if there's more than T1 faults, and I'll count faults and exclude them if there's more than T2, then we'll have a common feature protocol state as long as there's less than the minimum of T1 and T2 faults. So with the consensus safety proof works kind of just the same, even when people are running at different fault tolerance thresholds, but you have to kind of use this minimum of their fault tolerance thresholds rather than using any one of them. So the justification for the subjective fault tolerance threshold is mostly economic to me, but also it's a kind of a elegance thing. When you have an in-protocol fault tolerance threshold, that creates focal points for cartelization. So imagine you have a fault tolerance threshold of like F. Then what ends up happening is the cartel that has F has much less power than the cartel with with F plus 1. And then the cartel with F plus 2 doesn't really have that much power than the cartel with F plus 1. But then you go up to the cartel with 2F, and it has the same amount of power as the cartel with F plus 1, and then you go to 2F plus 1, and all of a sudden you have this max power cartel. So when you have an in-protocol fault tolerance threshold, as soon as you can meet the threshold of a little more than the fault tolerance to break it, or the quorum, or the Byzantine quorum, in order to the n minus t of them, then you have really a lot more power than if you had slightly less. So the in-protocol fault tolerance thresholds create abnormalities and step functions in the strategy space. They create clear focal points for if you're participating in a proof of stake system and you are, for example, a newcomer to a cartel and they already have 2/3 of the weight in there, your value that you're contributing to the commitment of consensus values is 0. assuming that they're connected and they're able to do it themselves. So you don't have much clout, actually. You're not increasing the fault tolerance of the protocol as far as they're concerned. You're not really contributing to the cartel. And so like the cartels like should be stable at like just over 2/3 plus 1 nodes. And kind of like imagine, for example, if Bitcoin were to tell you exactly how many confirmations to wait before reverting a block. It's before refusing to revert a block. So say like, okay, after 6 confirmations, we will refuse to revert. Well, then someone would like create a blockchain that's like exactly 7 long, do the minimum amount of work to cause consensus failure and like, to send it to people at the right timing, right? But if people have different numbers at which they decide not to revert blocks, then it's kind of much safer because like the protocol isn't so easy to attack because the adversary doesn't know what everyone's fault tolerance thresholds are. And this is also related to the liveness question around the kind of, why don't we use crypto for liveness? And the reason is like, I've never seen a way to do that doesn't require an in-protocol fault tolerance threshold. So like if you can find a way to guarantee asynchronous liveness without any in-protocol thresholds in terms of number of nodes required to move beyond some state of the protocol, for example, then that would be really cool and I would learn a lot. But I don't really think it's possible. But we'll see, but we never know. So the subjective fault tolerance threshold thing is something I really advocate for, but is, as far as I can tell, impossible in round-based consensus protocols. Any kind of protocol that says like, look, let's prepare then commit. Let's do 1 round and then another. Is going to have some notion of, look, this round is complete, which means that you have to have some in-protocol threshold, which I don't like for aforementioned reasons. And so, I'm actually a big fan of forking protocols with like arbitrary DAGs and no rounds, and I think that they provide an excellent alternative to commit to 2-phase commit protocols. But let's talk about liveness. So, somehow we want liveness in asynchrony, but FLP impossibility says we can't. And I kind of know we can't, because like I can always find a protocol state, so if I'm not safe, then I can find a protocol state on an opposite value which isn't safe. Then I can find a protocol state on the opposite value that isn't safe. So I could kind of know that I could be stuck forever if I allow any message arrival order. However, we have kind of seen. So we haven't actually said anything about when nodes are even trying to send messages. Actually, all we've said is like nodes have sets of messages as states, and like when they send a message, they say what state they're in. But we haven't said actually when they should send messages. So all of these questions about like what the nodes are doing when are kind of left out of the spec, which means that like we don't have a liveness proof, but also it means that we have a huge amount of flexibility on what the strategies are, and also and all of these are independent completely of the mechanism that guarantees consensus safety. So I don't have to struggle and worry about whether I lose safety when I'm trying different liveness strategies out. But we have seen in observations like the simulations so far that you do kind of end up finding safe states sometimes. And what this basically says is, look, there are DAGs which we can describe which do have liveness, which in the sense that like, if you manage to make that shape in the future, then you will decide on a new value. And therefore, like, if you have a precise message arrival order that you want to target, well, in a synchronous network, we kind of know how to do that. And in a partially synchronous network also. And so it's quite easy for us to construct quite trivially algorithms for guaranteeing safety. The other really nice thing actually is like, we can straight up say, look, do some proof of work, whatever, like any kind of consensus protocol that like ends up building a blockchain and you can show we'll do it in a partially synchronous network will be kind of enough for our liveness, and also won't factor at all into the safety proof. So there's there's like a big extent to which I can like literally go and like pick liveness proofs out of deterministic consensus protocols and use them without thinking about the safety side. So now let's talk about this whole overhead and performance thing, even though it's obviously I haven't said when nodes make messages, but I can talk about like the edge cases. And I can talk about this trade-off, which I think is like a really fundamental trade-off in consensus protocols. Basically says, you can only have 2 of 3 nice things of low latency, finality, low overhead, and large number of validators. I think it's like, really kind of unfortunate because we want all of these things, right? We want super low overhead, super large number of validators, and super low latency finality, but it's not going to happen. Traditional consensus protocols all kind of explore the trade-off over here on one side of the triangle, where they kind of try to get really low latency to finality, and they basically need to choose between having low overhead and a large number of validators. The more validators they put on there, the closer it gets creaking over, because the overhead gets so high, and the fewer validators, the lower the overhead. So if you want to have low overhead, low latency finality blockchain, you really have to have a small number of validators. Blockchains. Oh, and with all of these protocols, this is the friendly ghost. We can explore that trade-off by doing this kind of rounds-based approach, where we have like rounds of blocks, which can lead to things being finalized really quickly, but with a lot of overhead in terms of the number of blocks that are kind of orphaned. And so by doing rounds for every block, we can get really high overhead for a large number of validators, or moderate overhead for a small number of validators, but get really low latency to finality. With blockchain protocols, we normally do something like, we have something like no finality, but we have the same incredibly low overhead for any number of validators. Like any miners can show up, doesn't matter how many, any stakers can show up, doesn't matter how many, and still the overhead of the blockchain, at least after difficulty adjustment, should be the same. And so there's invariance of overhead in terms of the number of nodes. It's like really remarkable and something we've seen in blockchains, but has never ever been observed in traditional protocols. But typically no finality. What we see with like this kind of particular protocol execution of the same protocol as the one that we just saw in doing the rounds, is that we can achieve the same level of low overhead for any number of validators. But actually we can have, we can also have finality. We can also have like asynchronous Byzantine fault tolerant consensus, like, you know, decisions. And the basic, and so it's like quite cool because we get to have like somehow instead of being up, instead of being off the corner, we get to like jump right on there. And we actually have like, instead of a completely unbounded latency to finality, we have like bounded by like the number of validators latency to finality. Like, you know, big O, the number of validators. So basically, my kind of next claim is that like, look, we can actually try, we can explore the whole trade-off triangle with different DAG structures of these protocol messages, and I think that's like pretty cool. And like all I can really offer you for that in terms of visualization right now is this. It's kind of a random one. It's not really strategically trying to minimize the amount of overhead, but the number of blocks that had to be produced for this number of blocks of finality is still much less than if we were to do rounds of messages for every block and finalize them one at a time. And so this represents something like maybe in the middle of there of the trade-off triangle, where things are finalized a little quicker, but the overhead is higher. But we still get to have a moderate number of validators, and that's kind of the goal to me, right? That we somehow, I think that like the middle of this triangle is way better than there, and also way better than there. If you can have the overhead of your protocol by reducing your latency to finality by increasing your latency to finality by a factor of 2, I think a lot of people would take it, especially if they're running with a large number of nodes. And that's kind of the promise here. Great. So now we're ready for some sharding. But first, a water break. Any questions? Any questions? Yeah.
Finality. Why is it important to have like actual finality instead of some kind of probabilistic ones like in Bitcoin or any proof of work that deliver the block?
Yeah. So the question is like, why is it important to have finality rather than just a probabilistic one like in proof of work? And the main reason is that the probabilistic thing works as long as there's less than some number of Byzantine faults. Whereas when you have like real proper finality, when there's more than that number of Byzantine faults, you won't revert your blocks. So like when the mining, imagine if you just decided after 7 confirmations in Bitcoin, like 20 confirmations, there's never to revert, then like the cartel of miners could never revert more than 20 blocks. And that's safe enough, like 20 blocks, like I would recommend it, you know, just like set your thing, 20 blocks, like never revert if you can. because then you like, okay, well maybe you have consensus failure with everyone else who goes on the longer chain, but like odds are if there's a really long reorg, it would be it's like gonna be like basically finality represents a strong defense against reversion attacks because it like disallows reversion in the context of any number of Byzantine faults. If you're willing to assume that the network is synchronous and you won't ever have some number of Byzantine faults, then I think something like proof of work could, I mean, technically does work. But let me also say that like proof of work is not asynchronously safe, and that's like a separate issue. So it actually, it's not really clear how many Byzantine faults it really takes. There's a whole bunch of issues associated with proof of work, especially once you start thinking about economics. But in terms of like the specification of the consensus protocol, it's really great, really simple. All right, any more questions?
Maybe you can comment in very layman terms on the rightness in terms of decision power, right? So what, because I believe there are tons of stuff unsaid, very thesis-wise, but just like where are you heading in terms of, or maybe in this next slide, and please ignore my question, but like how do you really resolve, or how are you going to kind of like be more efficient, so to say?
So you're asking me how I can be more efficient? Are you asking about like how the protocols can be more efficient on network overhead? Normally, the way that's done is like, oh, we use a synchrony assumption and we make blocks and we make messages in a chain. It turns out to be like an incredibly low overhead way to do things, like for all of the consensus protocols, like whether it's integer or whatever. But it may not always be the thing that you want. Like for example, for the integer protocol, you want everyone to kind of give their initial guess and then do the median rather than to just try to minimize overhead by copying what the other person said. So overhead is, I mean, basically the way we do it is by targeting structures that have really low overhead. The interesting thing about forking, though, is like, okay, the fact that we have a forking protocol is the only thing that allows us to get overhead this low. But the fact that we have a forking protocol also means that the overhead could get quite high if our synchrony assumption fails, because you could have things revert multiple times. And so we're kind of this optimism that like lets us get really low overhead could also cause high overhead in the event of an asynchronous network. So it's not a free lunch, but it does look and sound cool. So hey. All right. So I guess let's talk about sharding now. So sharding is going to be actually, we're going to end up following pretty much the same process as before, basically because the safety proof says nothing about which protocol states nodes actually go through. It says it doesn't actually, it only just stipulates that they have a protocol state in common, doesn't require that they actually get there. And so we never actually had any requirement in our construction at all that all nodes decide on all values, or that all nodes see all messages, or that all nodes make all of the same decisions. All of that stuff is stuff you normally assume as being part of the consensus protocol, but didn't have anything to do with our construction in terms of the common feature protocol states, or in terms of the maintaining less than some number of Byzantine, in terms of the Byzantine fault counting. And so actually we're going to be able to straight up have a sharded consensus protocol without changing the safety proof at all, just by replicating a sharded data structure and not having nodes go through every protocol state. So it's really just going to be pretty much the same as before, only instead of doing like an integer or a bit or a blockchain, we're going to do a sharded blockchain. So sharded blockchains are actually very similar to blockchains. This is the current, this is like the very basic, the most basic setup that I really know. You basically have like blockchains on these things called shards, and these shards can sometimes share these things that are called merge blocks. Or we used to call them cross-shard blocks, but it's kind of long. And cross-shard blocks or merge blocks, they have this property that they have pre-block pointers on both shards, or any shards that they are across, and that they can be pointed to. So they can be a previous block of the shards that they merge. So they both point to shards that they merge, and they can be previous blocks of shards that they merge. So essentially, they can affect the state of a shard, and that shard can pick up on that written state and write on top of it. So it's not, so basically like they have pre-block pointers, and so they're considered blocks on that shard for the purposes of the pointers of blocks on that shard. So essentially we have this kind of crazy long block here, which is on both shards, and it acts as if it's a block on both shards, but it's gonna do some like cross-shard synchronization for us. Hope this makes sense, because now we got some equations here, and basically, just as before, we're gonna have like messages, have senders and justifications, but instead of writing all that stuff out, I just put that in D. D is the block data. It includes stuff like, for example, the sender and the justification, and maybe one day transactions. And I'm just kind of exposing the other stuff. And I used to give this kind of this definition where I start off with like the messages of height 0, and then define the messages of height 1, and then kind of take the limit. But now I'm going to use this like kind of more like recursive, like type definition type formula, so that I don't have to write a million lines. And so basically it says, look, a block on shard X, so X is like a shard identifier, includes like a little map from X to a block on shard X and some data, or it's a merge block that merges some set X, which is a superset of the singleton set X, or it's the genesis block on shard X. And then the merge blocks that merge some set of blocks basically have a bunch of pre-block pointers and some block data. So essentially, I'm just describing in kind of like math, like this type of situation where I have blocks that have pointers on multiple shards, and which can be pointed to by multiple shards. So the second line shows that, oh, look, we have pointers to multiple shards, and then the first line, that with the second term there, basically says, oh, look, like a merge block that merges shard X is considered to be a block on shard X, which is enough to let you point to it in this first part of the definition. Somehow it's like a concise way to give like the minimum type definition for this sharded block structure. So we have a fork choice rule for the sharded thing, and it's going to return a blockchain for every shard. So rather than like a normal blockchain, we take some set of blocks and we get a single block, which represents the blockchain underneath. We're going to take a set of blocks, and then we're going to get them for every single shard under a block. And like that block is going to be in that shard, and we're going to get, so basically for every shard, a fork choice. And this is kind of the fork choice, the sharded fork choice rule. Now, thankfully, like you're not going to need to evaluate it for every shard, but that's the function signature anyways. So you can say, look, I evaluate the fork choice rule for this protocol state and this shard and find this block. You don't have to go and evaluate it for every single shard. So we have this great thing that we're going to satisfy. It's called fork choice enforced atomicity of merge blocks. Basically says, look, the fork choice rule itself is going to make sure that these merge blocks are in the fork choice of both or neither of the shards that they're merged. So like the fork choice rule itself, this like thing that like isn't like that like may end up orphaning stuff and end up like like is like a fork choice rule. So like kind of as an estimator, it isn't strictly deciding. Is going to have this atomicity property, which means that like whether or not it's decided, the block, which is a merge block, is going to be in the fork choice rule of all of the shards that it merges, or none of them. So somehow the fork choice rule cares about these things called merge blocks, and it makes sure that they're atomic. This is the definition, right? And that's going to be useful because we're going to do cross-shard atomic operations, and we need atomicity for that because we don't want the call never arriving, or the money disappearing and never arriving, or never disappearing and arriving. But yeah, I'm happy to take a question. Hey, Daniel. Yeah. So, so actually, so there's a couple things. So one of them is actually like, the trickiness. I did do some tricky thing here, where like, oh, these are not actually pointers. This is just straight up nesting. And so we're not going to get any kind of DAGs, but you might get a situation where there's a kind of inconsistency. But you know, that's something that actually is not something I want to resolve at the level of the block structure, but that I resolve at the level of the fork choice. Basically, my fork choice will never choose that, but I allow it in the block structure. But yeah, that's a good question and good observation. Sorry, so I guess it was somewhat complicated, but basically we have a slide a little bit later that talks about this, and so I'll bring it up. So we have this great definition of cross-shard merge block atomicity, which is guaranteed by the fork choice. So this is as opposed to like all of the sharding solutions that do a multi-phase commit, right? Like a prepare and commit for atomicity. You know, I really believe, I've said this before, but I really believe in forking and safety detection as an alternative to two-phase commit. I don't think I think two-phase commit, two-phase voting protocols are like a thing of the past, and the blockchain kind of killed them with confirmations and forking. But it's going to take a long time for people to realize that, I think. But so somehow, I'm really proud of the fact that this fork choice, we got its atomicity across shards, and there's no phases. It's just done with this forking thing. Now we actually have some other, I'm going to share some other definitions, which aren't going to be satisfied by the protocol that I'm going to share, but which are quite cool. So we have this like notion of, remember we had this notion of safety of a property. Well, now we're going to talk about the property of a block being in the fork choice rule on a particular shard. And it says, oh, look, a block is safe on shard X if, for any future protocol state, that block is in the fork choice rule for shard X. And I use this little subscript to like denote which shard I'm looking at, both for the block membership operation and the fork choice rule, and the safety detection. And so then we have this like fork choice enforced atomicity of safety for merge blocks, which is a weaker notion. So rather than a block having to be like in both forks or neither always for any estimator, for any evaluation of the estimator, it needs to be atomic only if it's safe. So if the block is safely included in this shard, then it must be safely included in the other. If it's safely excluded in this one, then it must be safely excluded in the other for any shards that are merged. And this is kind of a weaker definition, which means that like, oh, we maybe take less overhead to guarantee it. And it's still quite strong. But then this is kind of like the weakest, I think maybe even the weakest possible cross-shard atomicity or like merge block atomicity criteria. And it basically says, if a merge block is included safely on this shard, then it can't be safely excluded on any of the shards that it merges. So I'm not saying that it's necessarily going to be included. It might not even ever necessarily be included. But at very least, no values that ever exclude it, or no alternatives could ever be decided on. So it could be that like this, if the shard, a block that merges my shard and yours gets in my shard and is safe, then what you can't safely exclude it in yours, you might never include it, but you can't safely exclude it. And I think this is like the weakest definition of atomicity that is kind of tenable in the sense that it just falls short of like breaking where you have like it's safely included in one shard and safely excluded in the other. Because the whole point with these merge blocks is that they're going to be at least eventually in the fork choice rule of both shards that they merge or neither, because otherwise we're not gonna enjoy the atomicity of the operations that are conducted in this block. So now we're going to get a little closer to the spec that is going to satisfy the fork choice and forced atomicity of merge blocks. We're going to restrict things a lot now. We're going to only allow merge blocks between shards that are connected by an edge in this binary hierarchical structure. So the root node can merge with those two. The nodes in the middle can each merge with 3 different shards, and the ones in the bottom only have one shard each that they can merge with, which means that they can only have, there's only one other shard that they can have a block in common with. And basically, the hierarchy is going to work such that the blocks in the shards, the fork choice rule of the shards that are lower in the hierarchy are a function of the fork choice rule of the shards higher, but not vice versa. So the ones in the higher in the hierarchy kind of strictly dominate the like earlier one, the ones lower, and the lower level shards get to just ignore what the higher level shards get to ignore what the lower level ones are doing. So basically, the shards that are lower in the hierarchy are going to be guaranteeing the atomicity with the merge blocks that get into the higher chain. So basically, imagine that we have this parent shard on the left and child shard on the right. And now instead of drawing the merge block as a big rectangular thing, I just drew this arrow, this line, which says that they're the same block. Sorry about that. I did this before I figured out the rectangle thing. Actually, before someone told me about it. So imagine that the block there, the merge block, is the most recent one in the fork choice rule of the parent. Then the child starts their fork choice rule there. So like the fork choice rule of the child starts at the latest merge block in the parent's fork choice. So definitely, if the merge block is in the parent's fork choice, it will be in the child's fork choice. For the latest one. And moreover, if the merge block is orphaned, then it will also be orphaned by the child chain. So the child will reject the block if it's an orphaned merge block. So the child has to be mindful of the parent's fork choice, and if they, in their current view, haven't included a merge block, then it must also not be included in the fork choice of the child. And this guarantees the other side of the atomicity, which, namely, if it's not included in the parent, then it also won't be included in the child. So we kind of have our atomicity, right? If it's included in the parent, then it's included in the child, and if it's not included in the parent, then it's not included in the child. And there is slight caveat, which is related to Daniel's question, which I think comes up in the next slide. But firstly, note that, okay, well, the child shards are kind of like at a loss for when the parent shard orphans blocks from their chain. So the child shard might have initially had those two blocks on the left in the chain, but then a new merge block was created, and because it got into the fork choice of the parent, orphaned those two blocks. So the child shard kind of strictly has less security than the parent shard, because the parent can orphan stuff that's after the most recent block that it has with the merged with the parent. And this is kind of related to Daniel's thing. Another kind of requirement, which is kind of super important, is that like if you make a merge block with a shard that you've already merged before, and you're the parent, so if you include in the fork choice rule, so the parent's only allowed to include in the fork choice rule merge blocks that are later than the previous merge block that they included for the child. So it's a little convoluted, but basically like the picture says it all. If you really, the parent has to be nice and always point to a later block than the block they pointed to previously. So if like I have a merge block and then another merge block in the same parent shard chain, and it merges the same other shard, then like it has to be that like it merges it at a later point, as opposed to, for example, trying to orphan something else previously merged. So in the second case here, like before that top merge block, the child shard would have started its genesis block on the right there. And then and somehow like something that it took for granted ended up, and that merge block is still in the parent chain, right? Ended up somehow being orphaned by the parent in the second case. And so like we don't allow that, because like that kind of ruins our property, right? We have to make sure that like the blocks stay in there. And so the parent has to always choose later blocks for the child. Cool. So basically, we have this binary hierarchical sharding, where we have the fork choice rules of the chains higher in the hierarchy determining where the fork choice rules start and what they must exclude lower in the hierarchy in order to guarantee the atomicity of cross-shard blocks, or these merge blocks. And basically what we're going to do is we're going to assign validators to a branch of the tree. So every validator is going to have n, so for like a single validator slot, at least in this like first spec, right, has n, has to be on n blockchains, like the root, one at level 1, one at level 2, one at level 3, and then one at level n. And so they have to execute all the, you have to execute the fork choices of the parents, or all of the ancestors, to do the to actually execute the fork choice rule of the descendants. But because it's like a tree, you can just like kind of pick any branch, and you can kind of fully do the fork choice rule for any child by just doing the branch from the root to the child. And so we have like 2 to the n minus 1 shards, with every validator only validating on n of them. So and kind of like the neat thing about all this is like all of this is still actually defined inside the correct by construction kind of framework, because the notion of an estimator is our fork choice rule, which we'll like think about safety about, which we can reason about safety on. And our protocol states are like still sets of messages that exhibit less than some number of faults. The only kind of difference now is that we're being a little bit more specific about what protocol states a validator can run. We're gonna mention like, oh look, these protocol states correspond to like being on these shards. Those protocol states correspond to being on those shards. And but in terms of the like actual mechanics of the proof, nothing has really changed at all. We're just replicating a different kind of data structure, one that happens to involve a bit of concurrency. So that's kind of the basic overview of like a very first sharded consensus protocol specification. And it is notable that this is actually sharding the consensus protocol as opposed to sharding a data structure and still having a same single-threaded consensus protocol in like the way that a bunch of people are experimenting with sharding today. Sharding consensus means that like you have actually like a sharded distributed consistency property. You have like or you interpret your distributed consistency property in a sharded way. Normally we think about deciding on all the values. Now we just decide on consistent values, even though we don't all decide on all of them. And you somehow I'm pretty excited that I was able to do all of this sharding inside the same proof framework. And I'm excited for all of the future iterations of these protocols. So let's talk a little bit, or first, breather and water break. If you have any questions, now is also the time. Yes, Mustafa.
Hey, so under your binary hierarchy sharding model, how can you do cross-shard transaction between two shards that don't have a parent-child relationship?
Great. So the question is like, okay, how do we do a cross-shard transaction between shards that don't have a parent-child relationship? And the answer is, well, the only infrastructure that we have to provide it is through the parent-child. And so right now the way that'll work is, you literally have to wait for routing through the structure. That said, there's a lot of future work around making this better. But this kind of it really, I think, does get significantly better in a number of ways. Like one of them is, okay, like that. You can imagine that like we're not stuck to the binary sharding. We can have a dynamic tree structure, which I'll mention also a little bit, and also load balancing, and also there's kind of there's some research on like a kind of trying to do allowing merge blocks much more freely. And it's totally possible. The thing that becomes a lot harder when you allow free merge blocks is guaranteeing this nice isolation of state transitions so that validators don't have to do more than some amount of work. And so I would say that like research on making like synchronous calls across all of the shards with fork choice and forced atomicity is still early stage, and please join us. You can do it. Okay, so basically we got some future work just on the correct by construction kind of framework and process. Basically, actually this protocol state structure of like sets of messages that exhibit less than some number of Byzantine faults is kind of a crazy thing, and I think that there could be a lot of research done on the structure of this like category or graph. We need to think about liveness strategies, measures, and proofs, and basically there's a lot of room for lots of flexibility there. Validator rotation right now I've only really done for the friendly ghost. Decided to leave it out of my talk today. I don't know why. I thought it was maybe too long. We're gonna try to work out how to do validator set rotation in the abstract as opposed to as a function of the blockchain structure, which I'm pretty hopeful about, and also without in protocol fault tolerance thresholds, of course. And then basically, we want new and more efficient safety oracles. Right now, for example, I don't have a safety oracle for the integer with mean. Like if I use the average, my safety oracle doesn't work because like any one minority node can change the average, and so my safety oracle's assumptions don't hold. And so, but I could potentially imagine having a safety oracle work out where I say like, oh look, the estimate is bounded between like 20 and 10, even though it might oscillate forever between there. Coming up with different oracles for different systems is kind of interesting. Maybe having, because it's a protocol that actually, instead of returning values of the consensus, actually does return these propositions about the consensus. That's potentially quite interesting because it like raises it to another level of abstraction. It means that we can potentially talk about stuff like, like real numbers. Like, you're never really gonna give me a consensus on a real number in the sense of like give me a value, but we could talk about propositions on real numbers all day. For sharding, we basically need to like think more about like this idea of like how are validator duties separate, and like what are the different protocol states that they like are transitioning to as a matter of like validation, and making sure that like their overhead is always bounded. There's actually trying to build a protocol that satisfies the really weak merge block atomicity definitions is totally interesting, and I think relatively open because I don't know that I have a solution, and I don't know anyone else is working on it. But definitely a cool thing. Also, the dynamic shard structure stuff is really cool. Like the whole changing the shard tree and moving shards around to do load balancing and to, for example, this idea of like temporarily isolated shards that like can't merge for a while and then can merge again and then can't merge for a while and can merge again, are the kinds of things that like will really lift the ceiling in terms of the scalability limits on this thing. Heterogeneous sharding is another interesting idea that maybe we want shards that make different trade-offs in this trade-off triangle. Maybe we want some shards to have really low latency to finality. Some shards maybe we want a really large number of validators, and how to think about maybe having different shards with different properties. There's also non-research work like education and implementation. There's a lot of it. Definitely could use the help. Definitely ready for help. There's and so basically like we have a prototype. It's in the Ethereum/CBC-Casper repo. We've implemented the binary consensus, the integer order on a list with fixed elements, a blockchain, a concurrent block schedule that spends UTXOs, and the binary sharding with the cross-shard atomicity that I just presented. So we have a bunch of these things implemented as basically just different modules in the single implementation, because like they really are just the new specification of the protocol message and the estimator. The rest of the code base is like stays the same for the most part. And so like, I think, like working on the prototype, maybe one day making a test set, and maybe one day going into production is a lot of work, future work, and we definitely need help. Basically, the conclusion, I hope, is that it's pretty cool, and that, you believe me that we're able to define lots of consensus protocols without doing much case-by-case analysis by just benefiting from the correct by construction framework. I think we can explore lots of trade-offs here without talking about the Byzantine fault tolerance or the asynchronous safety at all, which gives us a lot of ability to iterate fast, and which I think is also related to why like our progress in this kind of research has been accelerated. There's all these terms and definitions are laid out, and hopefully we're going to become more and more well documented so that you guys can come in and contribute, come up with your own consensus protocols or safety oracles or whatever. Don't be shy. So here we have some documentations. We got some tiny URL links here to the papers and both early drafts and the code base, and we have a Gitter, which I found out about yesterday, embarrassingly enough. So thanks a lot. And thanks ECC for giving me so much time to talk about Casper. Woo. The question is like, is there a degree of like concentration of holdings as required for CBC to work? No, I mean like so the main reason why that might be the case would be presumably what you're thinking about is like, oh, there's only a limited number of slots available. Yeah, and that does depend on what we choose in terms of this. Am I stuck here? In terms of the parameterization on the triangle, right? If we decide that we don't care about latency to finality at all, like 0, and we're just happy to be on the order of the number of validators who show up, then the barrier to entry could be very low. If actually we want a latency to finality that is on the order of hours or minutes, then the number of validator slots that we could reasonably tolerate for any given, without huge overhead, is much lower. And so it's a difficult question because it depends on like a parameterization that I don't know about. But I'm happy to say that I can make that parameterization, and that like if it turns out that people care much more about the barriers to entry being low than about the latency to finality, then that's conceivable that that's totally possible inside with the same protocol. Cheers. Yes. The question is, how long have we been testing on the testnet the sharding? And how long is it going to take to get on mainnet? Well, we don't have a testnet for sharding, or at least this correct by construction sharding. We just have a prototype, which is still something. It's still an implementation, but it's not distributed and it's not, ready for mainnet yet. When? I mean, soon. I mean, I don't know. Who knows? Anyone else? Yeah. Hi, Dan.
So another question is that if you have a transaction that involves multiple shards, is there an upper bound? I mean, there is obviously, but what is the upper bound for it to finalize on both? Like if it's just 2 shards, if it involves 2 shards.
Sorry, so you're asking about the upper bound on what?
On the transaction for the state to finalize both shards.
Upper bound on
On the number of blocks.
overhead? Oh, latency. Latency. Okay. So the question is like, what's the upper bound for latency of finalizing a transaction that affects multiple shards? So it depends on where. In the hierarchical sharding, it depends on where it is in the tree structure, because basically the root needs to finalize merge blocks on its children in order for them to be finalized. And so if you're really close to the root, it happens faster than if you're further down. But it's really hard to give any kind of block count, because like all of my definitions allow any number of blocks between any 2 merge blocks, and I don't have any sense for that from like, because there's.
Does it linearly increase with the number of shards?
No, definitely not. Definitely sublinear in the number of shards. Linear in the number of layers to the sharding, if you are at the bottom layer. Yeah, logarithmic in the number of shards. Yeah, absolutely. Yeah. Hello.
What's your opinion on regarding the shards localization? Like, it would be nice to have low latency, right? That small shard, and in the same time between safety, like something happens there, breaks the line. The shard needs to be geographically distributed. What's your opinion on this?
Yeah, so so the question is like, what do I think about like shard locality and the idea of like having like custom shards as opposed to like drawing everything from the global pool and trying to be as safe as possible. It's quite tricky. I mean, basically there's a couple of issues. One of them is like, are the blocks produced by this shard like available and valid? And if we kind of trust that they're valid and available, then building them, doing cross-shard transactions with the rest of the system is not impossible. However, we do need to make sure that they're valid and available. And if anyone can set up a shard with any nodes and just like do atomic transactions with the rest of the system and their blocks are not available and valid, then we may have a real problem. And so it's mostly, I think, about the in terms of the architecture, the biggest barrier to putting strange shards into the system is their the validity and availability of their blocks. I think it's conceivable, but I would say it's like still like, you know, I mean, you're asking about the release date in your last question, and now you're asking about something even further down, right? That's a good question. That's a whole can of worms. How do we determine the availability of blocks? Yeah, that's a ask Vitalik. No, no. At the moment, we have just like at least in this specification, like the shard structure is like part of the value of the consensus. There's like and it's just fixed. So there's no. I have like assignment of validators to shards, but I don't have like any nodes able to create and destroy shards at the moment. And basically, ultimately, you could imagine that kind of thing happening, but it's definitely not short term. You know, we gotta take baby steps. And you know, even though baby steps get bigger, it's still. Baby steps are great. Yeah, they're super necessary. I spent 8 months or something on the binary consensus before I had any like other consensus protocols.
So, is there a way that this sharding system will interfere with the transactions and contracts in the cross-chain field in the future?
So, is there any way that this sharding feature will interfere with transaction contracts in where? Cross-chain, meaning across different. Yeah, well, so whenever you're doing any cross-chain operation, you really should wait for some kind of finality on both, right? And you can detect finality when you're even doing an operation on a single shard. And so it's very similar to normal cross-chain kind of reasoning. Either you wait for finality or you have to like fork your application to match everything. And if you're trying to interoperate 2 chains which aren't forking to keep track of each other, then you really just gotta wait. I'm really not into side chains. Yes.
Do you think liveness is something you can accomplish with the current proof?
Do I think liveness is something I can accomplish with the current proof? Well, the proof is a safety proof. I think I could accomplish Sorry? Oh yes, absolutely yes. While keeping the current proof, yeah. I'm sure that I can accomplish liveness while keeping the current proof because the current proof says nothing about when nodes send messages at all. It is completely asynchronous. It just talks about sets of messages. There's like, it just I think that the safety proof is completely independent of the liveness strategy, and I love to keep it that way because it makes me really scared when like the safety of a protocol is like the same as as secure as the liveness of a protocol. Yes, Rob.
How do you actually, can you reason about safety of shard blocks under like a weight-based safety estimator? Because the only shard that can have a majority of validators on it is the root, right?
No, so actually you can have like even like a tiny subset of the validators on the root and then like some other tiny subset on these other shards. There's no real requirement that there be everyone on the root or something. I do like to put everyone on the root, but there's no real requirement for that. It's just that the framework to recognize is like, okay, well, you don't need to worry about arbitrary reversion of blocks, even if it's a small amount of weight on the root, because with these consensus protocols, instead you worry about consensus failure, which is like different from block reversion. And so you can have your blocks be safe, and like you can tell that they're final. Doesn't mean that someone else hasn't finalized something conflicting, but like the finality doesn't go away because of some number of Byzantine faults. So like it's not the case at all that like the root can revert finalized blocks from chains down the row. It's basically like any consensus protocol that makes a decision can't have their decision reverted by any number of faults, And you can have like any set of consensus forming nodes make the decisions about what blocks are in the root as far as Byzantine fault tolerance is concerned. Now, if you're economically speaking, like I wouldn't want to put a really small validator set in the root. But in terms of just Byzantine fault tolerance, it doesn't matter. It could be an independent set, it could be disjoint sets on every shard is fine. Just because of like the fault tolerance thing is, I mean, it's kind of a sledgehammer. It just says like, oh look, at least this number of nodes are going to behave well no matter what. And so like the root will like, so basically like, you know, if the root is finalizing stuff, then it won't revert that stuff. If it's finalizing inconsistent stuff, then like, you know, those inconsistent things won't be reverted, but someone might have to like hard fork or UASF to sync up with everyone else. So it's like the classic kind of like trade-off or like the trade-off between like always being able to have a common feature with someone versus actually making irreversible decisions. You can always have a common feature in something like proof of work because you can always see the same set of blockchains, but you can also revert any number of blocks. And so if you imagine like doing this in a proof of work system, then like a reversion in the root shard could lead to arbitrary reversion in the lower shards. But in like a system with any kind of finality, that's not so straightforward because it doesn't revert, it's just that people have consensus failure. Sorry, I didn't catch that. Is that what?
Just following on that, do you think it's a good idea to, instead of doing reversal blocks, the decisions could actually imply proposing new blocks with corrected states, to do kind of error correction on states?
Right. So that's actually a good question. So no. I mean, it's actually legitimate. So the question is like, okay, well, rather than doing reversion of blocks, maybe what we do is we like do new blocks and like correct the earlier state. Yeah, it's a very interesting idea, and it's one I used to be a big fan of. I used to do this like for my old sharding solution. I would have like one step where we kind of just like log things as they come in, and then another step where you schedule them. And then you have some execution, and that I think maybe is going to be useful, but I'm not ready to like say like yes or no anymore. I don't really use it anymore now because like I'm pretty happy with the forking, and I don't think the orphaning is that bad because it's at the end of the day it's relatively the same amount of work. The only question is like basically like there's like this question of kind of what order does the inclusive ghost happen, where like if you have like a you could have like something that's early in the state be executed later or earlier depending on how you set up the rules, but I don't know, it's complicated. It's definitely like not a novice question. And this is basically like to just like play it out again. You're talking about like imagine if like the state transition function of a block knew about and executed like a kind of fork choice rule in order to deal with the reorgs of earlier stuff rather than actually orphaning the earlier stuff. It's kind of like it's kind of a take on inclusive ghost protocols kind of to the max. Maybe. All right. Any more questions? Yeah, sure. What? Why unicorn? Oh my God, it's my favorite Ethereum t-shirt ever made. I don't know, I didn't make it, but I like it. Okay, well, I guess with that, thanks so much. Really appreciate it.